So the second part of the diastrait computation is now to resolve the differential equation, which is d dv d theta square v equals minus 4 epsilon divided by the diffusion coefficient 1 minus I theta plus square root of I theta to the power of 4, with the conditions that v of pi equals 0 and v prime of c square root epsilon is also equal to 0. So this equation is now easy to integrate, because we need to integrate twice. So v prime of theta minus v prime of c square root epsilon, so this is by definition 0, will give us the first integral from theta to c square root epsilon of whatever we have here, d eta, and then another integration will give us v of theta minus v of pi, which is by definition 0, which is the integral from pi to theta of the integral from c square root epsilon to let's say a variable theta 1, right? And then what we need to have is this term here, which is 1 minus iu plus square root epsilon of iu to the power 4 du d theta 1. And using the classical exchange of the integral, we get this is equal to this with a 4 pi d. This is integration from theta to pi of pi minus eta d eta divided by exponential I eta minus 1 minus I eta square root epsilon, and this is to the power 4, and this is v of theta. And so what we need now to calculate to get the information about the mean escape time from the domain is to take for theta a point, any point located in the domain that is outside the boundary layer of the cusp. That is, any point here would be possible. So, and this is equivalent in the map domain into any point located in this part here, in this region where the domain is mapped. So for theta equals square root epsilon, then v of c square root epsilon will give us the mean first escape time from such a domain. So what remains to be done now is to estimate this integral as epsilon is small, when epsilon is small. And so for this, we are going to split the calculation into two integrals, one with pi and the other with this term here. And so let's now focus on the first integral with eta d eta. So we are interested now in estimating c square root epsilon pi eta d eta exponential I eta minus 1 minus square root epsilon I eta to the power 4. And so to estimate this integral, we are going to make the following change of variable: eta equals square root of epsilon multiplied by zeta, and we shall use now the following properties, that exponential of I psi of square root of exponential I zeta square root epsilon minus 1 divided by I zeta square root epsilon minus 1. So this can be checked, that this is a quantity which is of order eta square root epsilon. So that we are going to replace this term in here by this formula, such that this integral becomes c square root epsilon. So we have not to actually use the change of variable, so this is c divided by square root epsilon, and this now becomes just c divided by square root epsilon divided by square root epsilon. And what we will be left with is that so if we have here epsilon in front of everything, we have epsilon that is in here. The terms in eta, d eta, now can be written as square root epsilon square zeta d zeta, and then on the denominator we are going to have the approximation of the exponential minus 1 as I zeta square root epsilon, and then here we are going to be left with something of the order of square root epsilon, because the other exponential will be approximated by 1, and this is to the power 4, which leads to so all the term in epsilon are going to cancel out. So we have integration from c to pi divided by square root epsilon zeta d zeta, and then we have zeta here square root zeta square plus 1 to the power square, and then divided here by epsilon. And so we get then in terms of the limit, the approximation, so this can be written as a constant, a constant term plus any I haven't added all of these, but there are all terms here in square root of epsilon that enters into this calculation, and this is divided by square root epsilon. So in summary, the term 4 epsilon divided by d multiplied by this integral c square root epsilon pi, and this is the term here is the one that is in here, can be approximated as c divided by d square root epsilon. And similarly, it is no, I'm sorry, this is incorrect. There is no here terms in square root epsilon, because this is a constant that we're going to get. Similarly, the other integral, which is 4 epsilon divided by d, the integration from c square root epsilon pi d eta exponential I eta minus 1 minus exponential I eta square root epsilon. So in this case we are going to get a constant divided by d square root epsilon. So in summary, this is obviously the leading order term. As epsilon goes to 0, we have that the mean first passage time, which is I'm not going to change the notation calling v, because this is v of z, and z is exponential I c square root epsilon. This is of the order a constant. So here there is, so it is a constant divided by d square root epsilon. And the difficulty now is to understand what is this constant c, which has to do with the part of the domain which is outside the boundary layer of the cusp. So the ingredient that is necessary to do this is to use the compatibility condition, which says that the Laplacian u, which was equal to, so d Laplacian u equal -1. If we integrate this over the initial domain, we get minus the volume of the domain equals d Laplacian u, which can be transformed using the Green's function as integral of du dn over the absorbing boundary dl. And so what we are now going to do is to use this formula with the property of the derivative of v in the w plane. So what is dv dn? So dv dn at the boundary, the absorbing boundary, which is here. This is the image omega of the absorbing boundary. So we need to calculate here dv dn at this part. So the normal here is now pointing in this direction, and dv dn is actually dv d theta for theta equals pi. And this can be calculated. It is we can either use the direct expression for v, and this is given by minus epsilon divided by d, integration from c square root epsilon pi d theta, and the classical denominator, so this is here to the power 4, which is equal to minus a constant d square root epsilon. So now it is possible to calculate this constant c by looking at the expression here for this compatibility condition. If we map everything into the domain omega of little omega, w of omega, what we are left here with is d multiplied by dv dn, and then the actually let's write it du here dn, and since in the original domain the length here of the absorbing part d omega was epsilon, we just have here this epsilon. And now what we have to do is to relate the derivative of du dn to the one of dv, and this is possible by using the classical expression for the Green's conformal function, which is dv dy. So again, the normal derivative in this original domain is according to the y direction. You know, this was in the original domain. This was in the y direction, and this can be written as, so du dy is actually dv dw multiplied by dw dy, and this has to be taken at the point w equals -1. Okay, so I will leave this as an exercise of the an exercise. So this is exactly dv dw multiply by 2 divided by square root epsilon, such that the formula that we have now to solve is to plug this into here and estimate the constancy such that this is equals to d 2 so square root epsilon multiplied by du dn multiplied by epsilon, which now we can remove this square root epsilon and we are left with this square root epsilon in here. And so the calculation here allows us to precisely get the constant. So C equals omega divided by 2. So finally we get the following so the mean first passage time, which is u at exponential I square root epsilon at leading order, is going to be given by pi, the volume of the domain omega. So if I go back now to the scale variable, epsilon was epsilon divided by r. So this is now divided by 2d multiplied by square root epsilon divided by r, 1 plus o square root of epsilon. So this is precisely the mean first passage time it takes to escape from a cusp. Note that in contrast with the two-dimensional escape from a domain where the absorbing hole is not hidden in a cusp, where the mean first passage time in dimension 2 is a surface multiplied by log of 1 over epsilon divided by pi d. The effect of a cusp is to increase drastically the time, and this can be seen here in this square root epsilon. This was comment 1. And the second comment that I would like to give is that this calculation is obtained for a fixed radius of curvature. So we cannot let, for example, r going to 0 to push this formula. This formula will not be valid. R has to be fixed, and epsilon here is here the small parameter. So I would like to finish with the following references where the calculation have been provided. So for the first time in 2011, in the context of calculating diffusion and in a surface paved with obstacles. The similar calculation was also done in this article, where we looked at how long it takes for a Brownian needle to go around in a confined domain. This is the confined domain. The summary of this calculation can be found in this SIAM review, and the detailed calculation appeared in this SIAM multiscale modeling and simulation article.